So in this lecture, we're going to reverse the process of the previous lecture. We'll start with a quantum field and show how that describes particles, at least for a non-interacting or a linear field equation. And we'll generalize the procedure of quantization to include more non-trivial field theories. And we'll actually even compute our first few interesting physical quantities. Okay. So last time, where we ended up was we showed that if we wanted to describe non-interacting spin-zero bosons, that we argued that these needed to be described by a field phi of x that was an operator for every point in space-time that satisfied the KleinGordon equation. Okay? So now here phi of x is a Heisenberg operator. It depends on time as well as space. So it's a Heisenberg operator that acts on Fock space. And by the way, something you should notice, if we're now thinking of this as instead a quantized field operator, then we can see that this, the fact that the quantum field obeys the classical equation of motion here is, in a sense, can be thought of as Ehrenfest's theorem. Ehrenfest's theorem says that the the expectation values of operators obey their classical equations of motion. But in Heisenberg picture, the states don't depend on time. And so the only time dependence is here in the operators, and so the fact that the operators obey this equation can be thought of as Ehrenfest's theorem. Okay. So in any case, the most general solution to this is actually written down. Because this is a linear equation of a simple type, we can actually solve it. Okay, and the solution is, again, what we wrote down last time. It's basically an arbitrary linear combination of these complex exponentials that represent plane waves with some operator coefficients. Okay, so for any operator alpha of p, this gives a solution. This right here is just a Lorentz invariant measure, so we've chosen things to be Lorentz invariant, but the content of this is just that it's a arbitrary linear combination of these plane waves. Okay? And okay, so here the alpha of p's are arbitrary, but last time we saw that if we want this to describe particles, we want Fock space, and that means that we want these alphas to obey this commutation relation. So again, we're writing in this Lorentz invariant way. Okay? So now, from the point of view of the field theory, we're just saying, okay, here's a field equation, which we have, let's say, have this classical field equation. We promote phi to an operator. Then this is the most general solution. So far we're fine from the field point of view. But now from the field point of view is, where did this come from? Where did this commutation relation come from? Well, the claim is that this is equivalent to imposing the canonical commutation relations on our field. Okay? So let's understand this. Okay? So let's just compute, starting from this and this, let's go ahead and compute the commutators of derivatives of phi and phi. So we'll take the derivative of phi of x, commutator with phi of y. Okay? Now if we go ahead and compute this thing, what we'll get is we'll get minus 2i dp, okay, p mu, what do we get? Cosine, right, of p dot x minus y. Okay? So we can see that this is what we get just by plugging in this. And here, notice we have used the commutation relation of the alphas. Okay? So now let's go ahead and evaluate this for the special case where x0 equals y0. So we're basically evaluating it at the same time. But now, by Lorentz invariance, this is a completely Lorentz invariant thing. Really, this just means that any 2 points that are space-like separated, we can always take the times to be equal. So this is really a choice of frame for any 2 space-like separated points. Okay? And then let's also take this index mu to be 0. Okay? So that really means that, in a sense, we're taking this derivative to be in the direction that's perpendicular to the plane that that in space-time that contains these 2 points. Okay, so there's really a more Lorentz invariant way of saying this, but basically we're looking at equal times and looking at the time derivative over here. Okay, so what happens if we evaluate that? Well, if we write, then we get d0 of phi of x t, y of x and t. So we're evaluating an equal time commutator. We have this minus 2i. And now let's write out what this derivative, what this is. This is d cubed p over 2 pi cubed. Then we have our famous factor of 1 over 2 EP. That comes from the measure here. This is p0, which is again a factor of EP. And then we have our cosine p dot x minus y. Okay? And what we see is that these e's cancel, the 2's even cancel, and what we end up with is just minus I, and this this integral over p just gives us a delta function. So we get delta cubed of x minus y. Okay? So this looks very similar to a canonical commutation relation, right? If this was a momentum and this is a position, and notice that they're evaluated at equal times. Okay? Just for fun, let's go ahead and evaluate this same commutator right here for mu equals I equals 1, 2, 3. So in other words, we're evaluating it now for a spatial derivative here. Okay? So then what we have is di phi of xt phi of yt. And what is that? Well, our integral now is minus 2i. We have our d cubed p, we have our normalization factor, but now upstairs here we have pi times the same cosine. Okay? And you can see that this integral just vanishes, right? Because this pi makes it an odd function, right? This cosine is an even function of p, but this p is obviously an odd function of p, so this just vanishes. Okay. So anyway, if we look at these equal time derivatives, it's only non-zero in the time direction, and it's just a delta function here. Okay? And notice that this condition here, if we look at this equation here, this commutator, it's a local thing, right? Because this commutator vanishes for space-like separation except at coincident points here. Okay? All right, but here, what we've done so far is we've started from the commutation relations of the alphas and derived the commutation relations of the phis. We now want to turn it around and show that imposing this commutation relation on the phis gives us the commutation relation of the alphas. Okay? To do this, it's useful to define what's called the KleinGordon inner product. It's not really an inner product, but that's conventionally what it's called. Something that it takes 2 functions, scalar functions of space and time, f and g, and gives us a number. And it's given by the following formula. Okay, so let me explain this. Here we're integrating over space only, not space and time. And both of the functions f and g are evaluated at the same time. Here f and g are allowed to be complex, so I have an f star here, so this is a complex function of space-time. And this little notation here, the derivative with the 2 arrows on top of it, it's kind of a fun notation. It just means f star g dot minus f star dot g. Okay, so that's what this double arrow thing means. Okay? All right, so why define this thing? Well, it has some nice properties. First of all, it has the property that it is actually time independent if both f and g are solutions to the KleinGordon equation. So from the definition, it looks like it depends on time t, but it actually doesn't. So to see that, let's take dt of fg. Let's just compute that. Oh, and there was this I. This I is conventional. We'll see why it's there in just a second. Okay, so we have this d cubed x. Okay, and now let's just write out the various terms that we have. We basically have this combination, and now we're going to hit it with another time derivative. So we're going to get a bunch of terms. We'll get f star dot g dot plus f star g double dot, and then we'll get minus f double dot star g and a minus f dot star g dot. Okay? And okay, so some things cancel right away. The things where one derivative is on each of these cancels. And then these leftover terms with the double derivatives, we can simplify those using the KleinGordon equation because we're assuming that f and g satisfy that. And so that says, for example, that f double dot is equal to gradient squared minus m squared of f, and the same thing for g, since we're, okay? And so if we plug that in up here, then this becomes, sorry about that little cross there, d cubed x. What do we get here? We get f star, and then we get grad squared plus m squared g minus, and then this f star becomes grad squared plus m squared acting on f star, sorry, this f star double dot, all times g. Okay? Now if you look at this, the terms with m squared obviously vanish because it's just f star g and then a minus f star g. The terms with the grad squared also vanish because we can integrate by parts twice, and so this whole thing is then just 0. Okay? So the time derivative of the KleinGordon inner product vanishes if both of these functions satisfy the KleinGordon equation. Okay? Okay. We can see another useful property of this KleinGordon inner product if we compute it for plane wave solutions. Okay? So let's compute it for two plane wave solutions, e to the I p dot x and e to the I minus I q dot x. Now here I've chosen e to the minus I p dot x so that if p0 is bigger than 0, this is what we called before positive frequency. Okay? So in other words, it would be the time dependence that we would have for a positive energy solution in quantum mechanics. Okay? But here in general, p0 could be positive or could be negative, and the same for q. Okay? So anyway, if you go ahead and do this, what you'll find, just plugging in, you'll find to the previous formula, you'll get something like this: 2 pi cubed delta cubed p minus q. Okay, times you get a complex exponential e to the minus I p0 minus q0 t. Okay, so this is just from the fact that basically the x derivatives of these things give me a delta function, so that's where this thing here comes from. Okay, now we have several cases. One case, let's look at the case where p0 and q0 have the same sign. Okay, if they have the same sign, remember both of these are solutions to the KleinGordon equation, and this delta function enforces the 3 momenta to be equal, right? So that actually means that, just from that delta function right there, it means that q0 has to be equal to plus or minus p0, right? They're the same, the 0 components, or the energy components, are the same up to a sign. So let's suppose we have the same sign, then this thing is non-zero right here and gives me a 2 e of p, right? And that could be either plus or minus depending on whether p0 or both p0 and q0 are both positive or both negative. So that's this sign. And then I get my 2 pi cubed and my d cubed p minus q. Okay? But now, because p0 and q0 have the same sign, this exponential vanishes. Okay? So I get something that is non-zero that's equal to plus or minus this thing right here. And this, of course, you should recognize, right? This thing is, if p0 is bigger than 0, this is just the inner product of two states. Okay? And if p0 is less than 0, it's just minus that same Lorentz invariant delta function. Okay? So here we see, for example, that this is not really an inner product because it's not positive definite. It is negative if both of these solutions have negative frequency. Okay? And the other case we have to consider is where p0 is equal to minus q0. They have opposite sign. Okay? In that case, this thing is just 0, right? Because these guys just cancel each other, and that's it, okay? So we can sort of see how this could be useful. This thing right here, basically, things that are positive frequency and negative frequency solutions are orthogonal to each other, in a sense. Positive frequency solutions have positive norm, and negative frequency solutions have negative norm. Okay, so that's why this thing is useful. Okay. Now, as you can sort of see from this result right here, the result actually looks Lorentz invariant, even though the definition of the KleinGordon inner product didn't look Lorentz invariant. Now, you can actually show that it is Lorentz invariant. I'm not going to pause to do that. It's not crucial for what I'm going to be talking about here, but you can actually show that. Okay? Good. All right? Okay, so what is this good for? What this is good for is we can use this to project out the creation and annihilation operators from our free field. So if we look at e to the minus I p dot x, and then we look at phi of x, right? We take the inner product of these two things right here. This thing is just going to be alpha of p. Okay, if we look at the, use the formulas that we just derived, okay? And if we take, and here I'm assuming P0 is bigger than 0, okay? So I'm taking an on-shell positive frequency solution here. And we can take a negative frequency solution, which is perversely e to the plus ip dot x with phi of x. And that will just give us minus alpha dagger of p, okay? And the reason for the minus here is because the derivative acts on this p with the opposite sign here. So if you go back to our previous equations, you'll see that there's actually a minus sign here. Okay? All right, and so now I have these formulas, and I can just go ahead and compute the commutator. So I can compute alpha of p, alpha dagger of q. Okay, and so what do I have? I have the integral d cubed x, and integral d cubed y. Okay, and then I have to put in these various these things here. I have to put in a e to the plus I p dot x and a d0, this two-sided derivative, times phi of x, commutator with an e to the minus I q dot y, time derivative here, phi of y. Okay? And what's implicit here is that x0 and y0 are both t, right? That, as per the definition. Okay? And now we can sort of see where we're going to get a non-zero result. These two operators are space-like separated, okay? And at space-like separation, phi commutes with phi at space-like separation, but phi commutator with phi dot is non-zero, right? So the only terms we get is where we have one time derivative here acting on the case where this time derivative acts here, and vice versa, okay? So if we work that out, I'm going to erase and write it up above. If we work out what that gives, this equal sign going to that equal sign right there, we'll get a d cubed x, d cubed y, and let's see, and then we're going to get a minus I p0, and then we'll have a commutator of phi of x, phi dot of y, that's our first term, and then we're going to get a plus I q0, phi dot of x, phi of y, okay? And let's see, do I have the sign right there? Yes, I think I do. And then I have my exponentials, because these exponentials here get left over. I have e to the I p dot x, e to the minus I q dot y, okay? All right? And now these commutators here, phi dot with phi, are just delta functions. Those are our canonical commutation relations. So remember, what is the logic here? What am I doing? I'm imposing the commutation relations between phi and phi dot at space-like separation and going to derive the commutator of alpha and alpha dagger. Okay, so on the left-hand side, remember, I have the commutator of alpha and alpha dagger, sorry, PQ, and I'm just go ahead and calculating that, okay? So now if I stick in those delta functions, and a lot of things will cancel out, and I will just get 2e of p, 2 pi cubed delta cubed p minus q, right? These turn into delta functions that allow me to do, say, the y integral, but then the x integral is just over exponentials. That just gives me this delta function, and so at the end of the day, I get the result that I wanted, which is that the familiar result that these commutators of creation and annihilation operators are these Lorentz invariant delta functions, okay? So what we've shown, again, just to hope it's clear, we are imposing this relation that phi of x, phi dot of y for space-like separation. So let me go ahead and write this out. X t phi dot of y and t, that this is equal to I d cubed x minus y, okay? We've just shown that this implies this relationship right here, okay? All right. Okay. Okay, so we've shown that this commutator, this equal time commutator of fields, implies what these commutators that we've got before by demanding that the theory describes non-interacting particles. All right. Now what we want to do is we want to take yet another look at this. We want to show that these commutation relation between the phi's follow from applying the rules of what we usually call quantization to this theory. Okay. Now, here comes a little harangue. Quantization really makes no sense whatsoever. Quantization is the process where we start from a classical theory and somehow derive from it a quantum theory. This makes no sense because really quantum mechanics is more fundamental than classical mechanics. The classical mechanics appears only as a limit of quantum mechanics. Certain quantum states behave approximately classical, right? And so really the quantum theory is fundamental, and we should be deriving the classical theory from it, not the other way around. So what quantization really means is it's a procedure to define a quantum theory that has a given classical theory as its classical limit. All right? Now even that is not quite right for what we're talking about. What's actually more important to us is that the quantum theory that we define has the same symmetries as the classical theory. Most notably Lorentz invariance. That's the key symmetry that we're trying to keep track of here. So, for example, right now we're talking about bosons, but when we talk about fermions, we know that there's no classical limit of a fermion field, right? There's no classical electron field the way there is a classical electromagnetic field. And indeed, when we go to quantize a fermion field, we will use anti-commutators. So we're going to have to make up a new rule of quantization, okay? And here, there's no question of getting the same classical limit. There is no classical limit. The only point of this procedure is that it gives us a theory that has the same symmetries, Lorentz invariance. So that's really what's going on, okay? Okay, so with that being said, let's review the standard procedure for quantization for bosons only. We'll do fermions later on, okay? So the basic idea is we start with a classical action, okay, which is defined in terms of a Lagrangian, L, okay? And then from that, we derive the Hamiltonian, which is at first a classical Hamiltonian, and then what we're going to do is we're going to make a quantum, derive from that a quantum Hamiltonian, quantum operators, including the Hamiltonian and other things. Okay, so we basically use the Hamiltonian, and the operators that appear in the Hamiltonian, the quantities that appear in the classical Hamiltonian get promoted to quantum operators, right? That's the basic procedure. Seems kind of Baroque, and when we actually do quantum field theory, when we do actual calculations, all of this machinery just completely fades away, and never is heard from again. But somehow it seems very hard to really formulate the theory without starting from this. Okay, there is this other way of formulating the theory in terms of path integrals, but it's much less familiar. So this is the only way, this is the best way, I think, still, the traditional way and the best way to make contact with what we know and to sort of set up a general quantum field theory. Okay, so let's do it. Let's start with reviewing the procedure for the classical case. So we'll assume that we have some classical variables, QA of t. So we may have, these QAs may be different components of the vector of a particle. There might be many particles. This A index just goes from 1 to n. That's the number of classical degrees of freedom that I have. And then I assume that I have some action, and the action is an integral dt of a Lagrangian, and the Lagrangian is a function of the q's and the q dots, okay? All right? And this action in general, we go from some t initial to some t final, all right? And the classical equations of motion arise from extremizing S subject to the conditions that the initial q is held fixed and the final q is held fixed. Okay? So we have, if we think of q's as some points in space, we have some q initial and some q final. We look at all the possible paths that go between q initial and q final. We find the one that extremizes the action. That's the path, that's the actually classical path, that's the path that satisfies the equations of motion. Okay? Okay, so let's just review how that goes. So what we do to extremize this, we think of taking an arbitrary trajectory, QA of t, and replacing it by a trajectory plus a small perturbation of the trajectory, delta QA of t. And we'll be working to linear order in this delta QA, okay? And because we're fixing the ends here, that means that this perturbation has to vanish at the ends, because this thing already goes from the right initial to the right final point. So we have to say that delta q of t initial and delta q, A of t final, those are both 0. The variations vanish at the endpoints. Okay? All right, and so then what we're supposed to do is we're supposed to extremize the action. That means we compute delta S, where delta S is just the linear term in S, the linear term in delta Q when we replace Q by Q plus delta Q in here, okay? So that thing is equal to 0. That gives us the classical equations of motion. Okay? All right, so let's just do it, okay? So let's write out what that is. Okay. What is delta S? Okay, so we go from t initial to t final. Well, the Lagrangian depends on QA. So there's a term, a linear term in QA, which is just comes from the dependence of the Lagrangian on QA. And then there's another term which depends on which comes from the dependence of the Lagrangian on the derivative, and this just gives us a delta t of QA. Okay? All right? And now what we want to do is we want to integrate this term here by parts, and what we'll get is dt del L del QA minus dt of del L del QA dot, and all of this times delta QA. Okay? Now when we integrate it by parts here, we have to actually check, there's actually a surface term that we get, which is evaluated at the endpoints here, t initial and t final. But it's easy to see that that surface term vanishes because of this condition here, that the variations, this is called the variation, right, this delta QAs, that they vanish at the endpoints. Okay? So now the condition is that this path is, that the action is extremized for general delta QA. So this is a general function of t. The only way this can vanish for a general function delta QA is for this to be 0 for each t, okay? And that is exactly gives us the Lagrange equations of motion. So the Lagrange equations of motion famously are del L del QA minus dt del L del Q A dot. Okay? All right. So hopefully this is a review. All right. So now let's apply this to a scalar field theory. Okay? So we're not going to change anything except the notation. So instead of having QA of t being my degrees of freedom, now I'm going to have phi of x and t. So I have a scalar which depends on space as well as time. So from this point of view here, this depends on time, this depends on time. Here I have a whole bunch of q's labeled by a. Here I have a whole bunch of phi's labeled by x. So I can think of there as being one quantum degree of freedom. Eventually it'll be quantum. Right now it's classical. There'll be one degree of freedom for each spatial point x. And if you think about what's been going on in the last couple of lectures, that should resonate, right? We sort of have an independent, we're going to end up with an independent quantum operator with every point x in space. Okay? All right. So the next thing we want is an action. Okay? So let's write down an action. So we'll write down d cubed, we'll write down an integral dt of something. And the d thing that we write a dt integral of is actually now an integral over space. And we'll have an action like this, phi dot squared. So how do I want to write this? Oh no, I want to write it Lorentz invariant way. D mu phi minus v of phi. Okay? Where did this action come from? I just made it up. Okay? So I am just writing down a simple action as an example for right now. Okay? We'll understand later why this is the action that we should write down. But for right now, I'm just writing it down. Okay? Now, I'm also going to include an arbitrary constant out front here. Okay? So here, v of phi is just a function of phi without any derivatives that is, for the moment, arbitrary. This right here is the simplest thing that I can write down that has derivatives of phi. This c, I've pulled it out as an overall factor. I could just as well write it in here and just rescale v. So you can think of c as being the coefficient of this term, if you like, okay? But I'm just having this arbitrary constant c out front. Now one thing that you can notice about the way I've written this right here is that it looks Lorentz invariant, right? This thing up here is, what is this? Remember, this is eta mu nu d mu phi, right? And what is that? That is actually phi dot squared minus grad phi squared, okay? So that's specifically what it is. But I've written it in a way which is this nice index notation, so it looks Lorentz invariant. Notice also here I've integrated over time, but then I'm also integrating over space. So at the end of the day, I'm integrating over space-time. So this all looks very, very Lorentz invariant, okay? Another comment is that I haven't told you what the boundary conditions are at early and late times, or what happens at spatial infinity. I haven't told you that. And I am frankly not going to be careful about that. Nobody's careful about that, actually. If you look at any book on or lectures on quantum field theory, we'll actually come back to this a little bit later when we're talking about perturbation theory. We'll do some sanity checks of this. But we're just going to assume that we can freely integrate by parts, that the boundary conditions are that the fields fall off fast enough at infinity, both spatial infinity and time infinity, that we can integrate by parts. Okay? All right. So now, as I said, this action looks Lorentz invariant, okay? But let's actually check that. Let's actually check that it's Lorentz invariant, okay? So this is a good exercise. So let's remember, how do Lorentz transformations act? Well, we looked at this in the last lecture, okay? If we take a field configuration phi of x, if we perform a Lorentz transformation on it, we're going to get a new field configuration phi prime, and it's also a function of x. What else would it be a function of, right? Okay? If we get old functions of x turn into new functions of x, okay? What is this new function of x? It's the old function evaluated at a new point, which is lambda inverse x, right? And we talked about the reason for this lambda inverse, okay? So now let's check. Let's check that this action is indeed invariant under this, okay? So to do that, it's useful to define a new variable y. Y is just this lambda inverse x, okay? And so now let's write the action, okay? Well, one thing that's easy is that we can see that d4x is equal to d4y, right? So when we write our action, we can write it as an integral over d4y, okay? And now, what about the other pieces of the action, okay? Well, we can see that, okay, sorry. Let me just look at let me look at the two pieces of the action separately. Let me first look at this piece of the action right here, okay? So that piece of the action looks like, before I do anything to it, it's d4x, v of phi of, phi prime, phi of, okay. What am I doing? Sorry, let me back up. Let me evaluate s prime. I'm evaluating s prime, okay? And there are two contributions to it, so I'll call them 1 and 2. 1 is the contribution from this term, and 2 is the contribution from this term, okay? Let's look at 2 first, because 2 is the easiest one to look at. So let me just put it down here, okay? Erase this stuff here. So what is this piece number 2? It is c d4 y, because d4x is equal to d4y. And then I have I have just phi of y, because that's what phi prime is. Phi prime of x is just phi of y. Okay? So this is the same as before, because y is just a dummy index. Okay? All right? If that was too fast for you, you should do this yourself on your own carefully. Okay? So let's look at piece number 1. Piece number 1, let me actually do that piece a little bit slower so that maybe that will help. I'll just write out what I have here. That piece is 1/2 del mu del by del x. Let me write it out completely actually. Eta mu nu d by d x mu phi prime of x del by del x nu phi prime of x. Okay, so the piece in s prime that comes from the first piece, I'm still integrating over the same x. I'm just replacing the phi's by phi primes. Okay, that's all I'm doing. Okay, but now this right here is just phi of y. This is phi of y, right? So to evaluate this d by dx of phi y, I need to use the chain rule, right? And so what is this? D by dx mu of this, if I just look at this piece, d by dx mu of phi of y will be dy rho dx mu times d by dy rho phi of y, right? Just using the chain rule. And what is this? Dy rho dx mu, well, remember y was just lambda times x, so this is just going to give me a lambda, excuse me, not a lambda inverse. So this will give me lambda inverse rho mu, and then this thing right here, this is d by dy of something y, I can just write that as d rho phi of y. Okay? All right? So using the chain rule on here twice, and let me go ahead and move up here, okay? So this is equal to, moving up, since I'm out of room down below here, c, and now this d4x is equal to d4y, and then I have my 1/2 eta mu nu, and then I get my chain rule thing here, which is lambda inverse rho mu, and I'm going to get another factor like that here, which will be lambda inverse, let's say, sigma nu, okay? And then I'm going to get d rho phi evaluated at y times d sigma phi evaluated at y. Okay? And now I look at this thing right here, and what is this? Okay? And you guessed it, using the defining property of Lorentz transformations, this is actually just equal to eta rho sigma. Okay? So indeed, now erasing this part down here, this piece here, this is piece number 2 in S prime, is C d4y, okay, eta, let's say rho sigma, d rho phi of y, d sigma phi of y. All right? And so y now is just a dummy index. I'm integrating over all y. Rho and sigma are just dummy indices, so this is the same as what I had before. Okay? So at the end of the day, what we conclude is that S prime is equal to S. S truly is Lorentz invariant. It looks Lorentz invariant, and it is Lorentz invariant. Okay? So that's it. All right. Okay. So now let's look at the equations of motion. All right. So we have our action. Let me remind you what it is. It's some constant d4x times 1/2 d mu phi minus v of phi. Okay, that's our action. And now we want to find the equations of motion for this action. So we take phi of x replaced by phi of x is delta phi of x, and we look for the linear term. When we make this replacement, we look for the linear term in S, and we require that that vanish. So the linear term is, we have our c out front, d4x, okay? So we have a 1/2, and now here we're looking at the first order term. We get 2 equal pieces when we take the linear term from this and the linear term from this. So we get 2 d mu phi, d mu delta phi. That's the linear term from here. And then from this term here, we just get a minus v prime of phi delta of phi. Okay? All right? And now, just like in the case of ordinary mechanics, we need to do an integration by parts. We want to get this derivative off of the variation, so we move it over here, and we get c d4x minus, now we have box phi minus v prime of phi, and we can factor out delta phi. So box here just means eta mu nu d mu d nu. It's just a shorthand, convenient shorthand. Okay? And now, by a standard argument, if this is required to be 0, this delta S is required to be 0 for arbitrary variations, the only way is if this thing right here is 0, and so we get our field equation like this. Okay? This is our field equation. Box phi plus v prime of phi equals 0. Okay? So, as a special case, if v was just equal to 1/2 m squared phi squared, then we just get the KleinGordon equation, the equation that we had before. But now we could also take v to have some additional, to have, say, other terms in it, higher powers of phi, for example, and we could get something else. All right? Notice also that here the classical equations don't depend on c at all. Okay. All right, that was our review of the Lagrangian equations of motion, and we saw an example of how we could do that for a field. Now let's do the next step. The next step is to go from the Lagrangian formulation to the Hamiltonian formulation, first in the classical case. So let's review the classical Hamiltonian. Here the idea is we first define some, so remember we have our variables QA of t, we're back to that language, okay? And so we define, for every q, we define a p, we define a conjugate momentum, and it's equal to the derivative of the Lagrange function with respect to q a dot, okay? And you'll notice that I'm sneaking in some upper and lower derivatives, upper and lower indices, and well, we'll see how that works, okay? So this is just a definition right here of the momenta, but it gives us an equation that allows us, in general, to express the q dots as some functions of the p's and the q's, right? Okay? So we assume that this equation can be inverted to give us the q dots in terms of these other guys. And then we define the Hamiltonian as follows. It's PA Q dot A minus the Lagrangian, which is a function of q and q dot. So far, this is now a mixed thing that depends on the p's and the q dots, but the Hamiltonian is defined by then taking this function and taking q dot to be given by this function of the p's and q's that I found up here. Okay? All right. So that is the Hamiltonian, and then the Hamiltonian has its own equations of motion. I'm not going to go through that because we're really interested in the quantum mechanics case. Okay? Let's just apply this now, just as we did the classical Lagrangian. Let's apply this to our scalar field theory. Let's see what the Hamiltonian looks like for that. To apply this to scalar field theory, it's useful to rewrite this relation in a slightly different way, to rewrite it in terms of the action. In terms of the action, we can write this as PA of t is the variational derivative of the action with respect to QA of t. Okay? All right. Oh, something I forgot to mention. Here, the indices are summed. Okay? And notice that I have an upper index and a lower index, and it's summed. This just becomes, after a while, at least if you're a particle theorist, this just becomes second nature. Okay? So yeah, I'm using the summation convention, and you'll notice that upper and lower indices have gotten summed here. Okay? All right. Okay, so back to field theory, I want to use this kind of a relationship right here. So in scalar field theory, I'm going to define my momenta, I'm going to call it pi of x, okay? And it is going to be the derivative of my action with respect to phi dot, okay? Phi dot of x, okay? And what is my action? Well, my action, okay, since I have x's here, and I'm going to call the dummy variable in my action something else, I'm going to call it y, okay? What does my action look like? Well, it had this function, this constant c out front, and then I had 1/2 phi dot squared of y minus a 1/2 grad phi of y squared minus I had my v of phi of y, okay? So that's what my action looks like. I'm taking the variational derivative with respect to phi dot. Well, that only hits this first term, right? All these other terms depend on phi and not phi dot. And so the only term that I get comes from here, and it's actually just equal to c times phi dot of x. Okay? All right? So pi, the conjugate momentum, is up to a constant, is just pi dot. Okay? And then I can plug into this formula here for the Hamiltonian, in this case, and what do I get? Well, the Hamiltonian I get here is I'm going to get an integral over d cubed x, and then I'm going to get 1 over 2c pi squared of x plus c times grad phi squared with a 1/2 plus v of phi, turns out. Okay, so you can do a little bit of the algebra. Okay? So now, notice a couple things. First of all, notice that this doesn't look at all Lorentz invariant, right? The action looked very, very Lorentz invariant, and it was. This Hamiltonian contains the same information. Remember, the Hamiltonian, the Hamiltonian equations of motion are designed to agree with the Lagrangian one, but it certainly doesn't look manifestly Lorentz invariant anymore. And that's just life. That's when we start with the Hamiltonian, we start defining momenta, and these have to do with time derivatives. Means we have to pick a direction of time, means we lose the manifest Lorentz invariance. Okay? Notice also that C appears here in kind of a non-trivial way. This looks a lot simpler if only we could choose C equals 1. But for right now, there isn't any fundamental principle from this classical field theory. Why should I choose C equals 1? Why should I choose it to be anything? I don't know. Okay? All right, so that's all I have to say about that. All right. Now let's look at the quantum theory. That's what we really care about, right? So in the quantum theory, what we're supposed to do is we're supposed to take the QAs and the PAs, okay, and turn them into operators, right? Okay, and these operators are supposed to satisfy the canonical commutation relations, QA PB equals I delta AB. Remember, h bar is 1, okay? And what this says is that if I have multiple degrees of freedom, A, B, and so on, that they are actually all independent. The positions in momenta corresponding to different degrees of freedom are independent, so they commute, but the ones corresponding to the same degree of freedom, they have this famous canonical commutation relation. All right? Okay, let's just make a word about Schrödinger versus Heisenberg picture here, because we're actually more familiar with Schrödinger picture. That's where most, when we do undergraduate quantum mechanics, it's usually pretty much all in Schrödinger picture. So in Schrödinger picture, remember the states are the things that depend on time. So I'll temporarily put a little s here to remind me that I'm talking about Schrödinger picture. And so there's some unitary time evolution operator that takes the Schrödinger state at time 0 into the Schrödinger state at time t. Okay? This is unitary, since we have unitary time evolution. And the operators, on the other hand, the Schrödinger picture operators, are just independent of time. Right? They're just the operators. There's nothing more to say. All right? Now, what does Heisenberg picture do? Heisenberg picture, you can think of as starting from this, okay, and where you now just take the time evolution out of the states. So you define a Heisenberg state, which is just U dagger of t acting on the Schrödinger picture state at time t. So at any time, I just do this, I just undo the time evolution. So this is always back to the Schrödinger state at time 0. And so the Heisenberg picture states are independent of time. They don't depend on time. But now I need the matrix elements of operators in these states to agree with the Schrödinger picture, because I'm trying to describe the same physics. And so the Heisenberg picture operators do depend on time, right? And they look like U dagger of t O Schrödinger U of t. Okay? And that's defined so that these things, these O of h's in these states, in the h states, give me the same thing as the s states, the s operators evaluated in the s states. Okay? And here I've chosen these two pictures to agree at time equals 0, t equals 0, but that's of course arbitrary. Okay? All right. So now let's go back. What does that mean for our commutation relations? Well, the way that you're used to seeing the commutation relations is in Schrödinger picture. In Schrödinger picture, they're good old honest p's and q's. They don't change with time. And if you compute their commutator, it is just a delta function. All right. Now, to turn this into a statement about Heisenberg operators, I just have to conjugate these operators by the u's. Okay? And it's easy to see that when you do that, this thing implies that the Heisenberg, Q, the Heisenberg Q with the Heisenberg P, okay, is equal to also just delta AB, but the crucial point is that these are evaluated at the same time, right? So when I conjugate any two operators with the same U, they're always gotten at the same time. So the point I'm making here is that following the rules of quantum mechanics that you know, when you look at them in Heisenberg picture, they tell you that the canonical commutation relations are imposed at equal time. Okay? That's the point that I want to make. All right? Okay? So now I'm going to proceed to drop all these H subscripts, because in quantum field theory, we're always going to be working in Heisenberg picture. Well, except when we're not. But anyway, for now, we're working in Heisenberg picture. And so let's see, what are the canonical commutation relations? So just instead of the QAs, we now have the phi of x and t's, and instead of the p's, we have the pi of x and t's. And so if we just put in what this relationship is, you know, I think I have this backwards. I think this is a minus. QP is minus, yes, okay, so you'll have to fix that, I think, in the previous one. QP is minus I, all right, okay. So if, now I'm going to write it this way, I guess, I've written it this way here. Pi of x and t with phi of y and t. So x not equal to y is like allowing a not equal to b up here, but I have to put them at equal times because this is the Heisenberg thing, and then this is I, and instead of a delta AB, this becomes a delta cubed x minus y. So just following, right. So this is just following the rules of quantum mechanics, okay, as we've said. Now, what is this thing right here? This thing right here is just equal to c times phi dot, right? That's what pi is. So we finally get the equal time commutation relations I over c delta cubed of x minus y. Okay? All right. So now, all right. Now, what happened? What's the deal with this c? Remember, this c was an arbitrary constant that I put in that normalized the action, right? And it didn't matter for the classical equations of motion; it just factors out. But it comes in here. So, but choosing different c's, if you work it out, remember that this commutation relation is, for free field theory anyway, is equivalent to the commutation relations of the alphas. So rescaling this commutation relation is the same as rescaling the alphas, which is the same as rescaling the states. So choosing different c's will just give us different normalizations of the states, which is no big deal, okay? So we'll always just choose c equals 1. It's just a choice for normalizing the states, and that's called just canonical normalization for the fields, okay? So that's our choice, okay. So what I want to explain now is that free fields, which we've talked about in the first few lectures, free fields are actually identical to a system of uncoupled simple harmonic oscillators, okay? So let's remember the action for our free field theory, T for x, and I'll write it this way. Okay? So that's our action. And you can already sort of see that something like this has to happen just from the fact that the action is quadratic. The action is quadratic in the fields. And so what else are you going to get besides a simple harmonic oscillator? But let's see it very explicitly. And to make it very explicit, what we're going to do is we're going to put this system in a box of size L. So specifically what that means is that I'll take the fields, phi of x and t, and I'll impose that they're periodic with periodicity L. So we'll impose that the fields x plus L e hat times t gives us the same field as x. So here E hat is just one of the unit directions, x hat, y hat, or z hat. So this is basically putting the system in a giant cubical box of size L. Okay? And eventually we'll be interested in taking L large, but taking L finite will make things, make the connection to the harmonic oscillator very explicit. Okay? And so in this situation, we can Fourier transform the field. So we start with fields which are functions of x and t, but we can write these now as a sum over all momenta, okay, of some coefficients, call them phi p of t, e to the minus I p dot x, okay? And so these here are the, I p vector dot x. I'm just Fourier transforming in position space these functions. And so these are now, these phi p's are just functions of t's, just like these phi's were function of t's. And it's useful to define this sum with a factor of 1 over volume, where the volume is just L cubed. That's the volume of our universe. Okay? And now because this is in a finite box of size L, this sum over p is really a sum. It's really a discrete sum because of the periodicity here. The allowed momenta are just given by 2 pi over L times a vector, where these guys right here are integers. the three components of the vectors are just integers. So this is really a discrete sum, okay? And yeah, this is just a discrete Fourier transform. And the reason that we've included this factor of 1 over volume here is that in the infinite volume limit, or the large L limit, this sum, 1 over v times the sum over momenta, just goes over to d cubed p over 2 pi cubed, the integral over d cubed p over 2 pi cubed, right? And you can see that because sort of the volume element here in this, because of, this 2 pi, this stuff, yeah, you can see where this comes from, okay? These factors come from, this is sort of the unit volume in momentum space is 2 pi over L, and you have to sum over all of them, okay? Okay, and while we're the subject of the infinite volume limit, look up here, if I integrate d cubed x e to the I p minus q dot x. So if I integrate just over the whole volume times this thing right here becomes just the volume times delta p comma q. So you can easily see that. So when p and q are not equal to each other, this is 0 because the phases just cancel. When p and q are equal to 0, I'm just getting the volume, right? And we know that in the infinite volume limit, looking at this side right here, this becomes 2 pi cubed delta cubed p minus q. Okay? So those formulas are useful because in the end of the day, we're going to be interested in the infinite volume limit. Okay? All right. So now if we just use this Fourier transform, which I've just now erased, if we just plug that in to our action, what do we get? We get, we can pull out the factor of 1/2 here. We still have an integral over t. And then we have a single integral like this. And then we will have a phi of p dot phi minus p dot, okay, plus we will have a p squared plus m squared. Actually, this is a minus, sorry. Let me write down here. P squared plus m squared, phi of p, phi minus p. Yeah, okay? That's what we get. So notice here that we get a phi of p and a phi minus p here. So where did this come from? Remember, this started out as a d cubed x integral. We plug in 2 Fourier transforms, but then the x integral can be done, and that makes these p's equal to minus p's here. Then we're left with one sum over the p's. So if you just do this, if this is not clear to you, you should do this yourself, but this is what you get. Okay? All right, now this looks kind of funny, right? It almost looks like a simple harmonic oscillator, except for this funny p minus p business here. Okay, but this actually makes sense if you think about it, because if you remember that phi of x is real, right, or Hermitian. Let me write Hermitian. Phi of x is Hermitian, so that means that actually if you go back to the Fourier transform, it means if I take phi of p and I take dagger of that, I get phi of minus p. Okay, so the fact that the original phi's were real and I did this complex Fourier transform gives me phi of p's which actually have this funny generalized Hermitian condition. So these things are just Hermitian conjugates of each other, and these are Hermitian conjugates of each other, and that makes the action real, as it should be, right? Okay? Okay, so, but there's a simple way to fix that, right? We just work with even and odd combinations of this. So we have phi of p even is just 1/2 phi of p plus phi of minus p, okay? And phi of p odd is just going to be equal to, if I want I over 2 or minus I over 2, I think I want I over 2 phi of p minus phi of minus p, okay? So with this factor of I here, well notice this is Hermitian because these are Hermitian conjugates of each other. This is also Hermitian. There's a difference of 2 Hermitian it's something and its Hermitian conjugate, but then the factor of I makes it Hermitian. So these are Hermitian or real things in the classical case, and they're just the even and odd combinations of this. And if I now go and rewrite my S in terms of these, what do I get? I'm going to get S 1/2 this, and this part right here turns into a sum over even and odd pieces. So I'll write that as sum of I equals even to odd. You can tell I'm not going to use this notation for very long. I wouldn't be carrying this around forever. I would use plus and minus, but we've already defined phi plus and phi minus. Anyway, we won't use this for very much longer, so don't worry. But anyway, if you do this, then what are you going to get? You're just going to get actually a 1/2 phi I p, phi I p, and this is dotted, minus, I've got the 1/2 out front, so I don't need the 1/2 here, minus e of p squared, phi p I, phi p I. Okay? So now it just looks like, literally like the sum of a bunch of harmonic oscillators, right? So for each pi, I going over even and odd, and p going over all the p's, I have a harmonic oscillator. Now there's one little slight subtlety here, and that is that really I'm just summing over half of the p's in order not to double count, right? Because this thing right here, phi of p, you know, this thing here is an even function of p, this is an odd function of p. I would be double counting if I summed over all the p's. This is not going to be the formalism that we mainly use. This is just trying to make as explicit as possible that it's a sum of harmonic oscillators. Okay? All right? Okay, so now that we see that this is just a sum of harmonic oscillators, let's go back and remind ourselves, okay, what was that about the harmonic oscillator again? How do we solve the harmonic oscillator? So let's talk about the harmonic oscillator in Heisenberg picture. As Sidney Coleman once said, that the career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing degrees of abstraction. And that's certainly going to be the case here. We're going to treat the harmonic oscillator in probably the highest level of abstraction that you can probably treat it. Okay? So, as I said, we'll work in Heisenberg picture, and we'll write the harmonic oscillator Hamiltonian like this. Okay, so P is the momentum operator, X is the position operator. This is just a 1D harmonic oscillator. I'm calling the mass capital M because it has nothing to do with the mass little m of the particles that we're describing. This is a completely different universe. We're just talking about the harmonic oscillator on its own. The spring constant, if you like, is K. Okay? So what is the Heisenberg equation of, what are the equations of motion here? Well, remember that in the Heisenberg picture, the operators right here are given by e to the I h t times the Schrodinger picture operator is e to the minus I h t. Okay, so I've temporarily put the, well, we could say this is the operator at time t equals 0, or it is the Schrodinger operator. Okay? And so from this you see that the equation of motion for the operators, if I just differentiate both sides of this, the Heisenberg operator is I, H, comma, O, just H, comma, O. Okay? This is the Heisenberg equation of motion. All right? So let's just check that with this equation of motion here, we get what we expect, namely that this should give us the equations of motion of a simple harmonic oscillator. So for x dot, we have to plug in I, we have to plug in the Hamiltonian, comma, x, but the only piece of the Hamiltonian that doesn't commute with x is this piece right here. So we can just write p squared over 2m. And then if we work out this commutator right here, we will just get let's go what, p over m or minus p over m? I guess we get p over m. Okay? Supposedly, if we use the right sign for the canonical commutator. Same here, we write p dot is I, and then we have to take the commutator of h with p, but the only part that we need to worry about is this potential piece here, the 1/2 kx squared, and so now we're going to get minus k x over we get these equations of motion, but now we can put these together. We can calculate x double dot by differentiating this. I get a p dot here, but p dot is given by this, and finally we get x double dot is minus k over m times x, which is as we expect. That is the equation of motion for x. Okay? All right. So now we're in Heisenberg picture, so we're trying to solve for the Heisenberg operator x of t. But because this equation of motion is so simple, we can just write down the answer. And it is just x of t is just a e to the minus I omega t plus Hermitian conjugate, where omega is just the square root of k over capital M. Okay? So this is just, we're basically following the same steps that we did at the beginning for field theory. We're following the same steps for the harmonic oscillator, and they look very much the same, right? Okay? So far, A here is an arbitrary operator, but now we have to impose the canonical commutation relations between x and p, and those then tell us that A, comma A dagger has a non-trivial commutation relation, which is, let's see, what is it? It is 1 over 2m omega, okay, if we work that out. And so because of this, it's conventional to define an operator little a, which is 2 square root 2m omega times big A, and then this thing has the simple commutation relation A, comma A dagger is 1. Okay? All right. And then we can do a little bit of algebra to write the Hamiltonian in this language, and H is then going to be equal to omega over 2 A dagger A plus A dagger. Okay, after a little bit of algebra, you will find this. Okay? All right, so as I said, up till this point up here, we've been following the same logic as we did with field theory. Now, however, now we've written the Hamiltonian, let's actually find the energy eigenstates of this system. Okay? So let's suppose that we're interested in the energy eigenstates, so we'll write this kind of equation right here. Okay? And now we're going to find out what these A's and A daggers do to the energy eigenstates. So to do that, go ahead and erase all this here. So to do that, it's actually a little bit more convenient to write the Hamiltonian in this form, just using the commutators of the A's. And now let's look at the state where A acts on an energy eigenstate. Okay? And let's compute the action of the Hamiltonian on that state. So using this formula up here, that is given by A dagger A plus 1/2 A acting on that state. And now what we'd like to do is we'd like to pull the, sorry, it's the other way around. It's A dagger A. Okay? And now what we'd like to do is we'd like to pull the A over to the left side of the equation. We can do that here just by using the commutation relation here. This is A dagger minus 1. Okay? So we see that if we just ignored this 1, we would just be changing the sign of these, changing the order of these two operators, and then what we would get would be nothing but the term A, H, E. We would have successfully pulled the A all the way over here. But there's this correction term, this minus 1 here, and that minus 1 gives us a minus, and there's an A here times E. Okay? So we get this formula here, but this, of course, is just E times E, because E is an energy eigenstate. And so what I see is that in the end, what I get is E minus omega times AE. So in other words, AE is an energy eigenstate with an energy reduced by an amount omega. Okay? So this is what you, in other words, A is a lowering operator. It lowers the energy by an amount omega. Okay? Now, this system must have an energy that's bounded from below. There has to be a state of lowest energy. Otherwise, the system is unstable well, otherwise the system is unstable. And so there has to be a state, an energy eigenstate 0, such that A acting on that state gives us 0. Otherwise, if there were not such a state, we could lower the energy without bound. Okay? So this is one state that has to be there. And then another set of states that has to be there is any state that we can get by acting on this one with any number of A daggers. So we can consider A dagger raised to an arbitrary power n acting on that state. Okay? And we will call, and we'll normalize that state by some normalization factor, script n sub n, and we'll call that state n. What else, right? We'll call this state n, which is labeled by the number of A daggers that we have acting on this. Okay? So now, having defined these states, we can compute their overlaps. Because if we take two such states, we want to compute mn, just using this formula down here. This is n sub m star, n sub n, times this 0 state with n A's and, sorry, I guess m A's and n A daggers. Okay? Now, this we can evaluate using the commutation relations. Okay? The general strategy is to move these A's to the right, where they will annihilate these O's, and we'll move them there using the canonical, or using the commutation relations. Okay, and so we can do that using this kind of a formula here. A single A commutator with n of these guys is actually equal to n A dagger to the n minus 1. Okay, now you can see that this is true for n equals 1. For n equals 1 it's true, and then assuming that it's true up to some n, you can prove it for n equals n for n plus 1 by induction. So it's straightforward to prove this by induction. So if we apply this formula here, then mn is equal to, let's see, we have our normalization factors n star n, and now what we're going to do, sorry, this is m and n. Okay, so what we're going to do is we're going to write this term right here as a sub. What we'll do is we'll write this as a sub m minus 1 times a dagger to the n. Okay, but then we can go ahead and replace this last product here by this commutator, and the reason is that the term that we've added or subtracted has an a on the right, and that vanishes when we hit the vacuum, or the 0 state. See, I'm calling it the vacuum. The ground state. 0 is really the ground state, right? It'll be the lowest energy state. And this commutator, on the other hand, is equal to n A dagger to the n minus 1. Okay? So making that manipulation, what we'll see is that we'll get an extra factor of n here, and then we will get a to the n minus 1, a dagger to the n minus 1. Okay? So in other words, we've pulled out a factor of little n, and we've reduced the power of both a and a dagger by 1. So now we can just keep going, right? That's the obvious thing to do, until we get down to the states where there are no more of these. And so then what we get is we get our normalization factors. Okay? Well, first of all, what we get is now, we can see if we keep going like this, if n and m are not equal, eventually we will run out of a's or we'll run out of a daggers. Whichever one we run out of first, it doesn't matter, we'll get 0. So if we run out of a daggers first, a acting on this will give me 0, right? If we run out of a's first, a dagger acting on this gives me 0. So this is only non-zero if m and n are equal. So there's a delta mn. Okay, and then if they're equal, you see I'm going to get an n factorial, because I keep getting a factor of n every time I do this. Okay, and so good. Oh, excuse me. So good. So we can see from this that the convenient thing to do is to choose this this normalization factor to be 1 over square root n factorial, and then if we do that, what we see is that the overlap mn of these states is just Mn. They're just orthogonal with unit, they're just orthonormal. Okay? And good, and now you can just compute in the same sort of way. You can now just compute with this normalization. You can see that if I actually take a dagger and act on this n state, because the normalizations, because of these normalization factor, I don't just quite just get n plus 1, I actually get the square root of n plus 1 here. And similarly, if I act with this lowering operator, I'll get a square root of n minus 1. So you can see that the raising operator just gives you the state n plus 1, the lowering operator gives you the state n minus 1, and there are these factors, these square root n type factors, come from the fact that I'm using states that are unit normalized. Okay? And then finally from this, we can finally see what the energy eigenstates are. So H acting on one of these n's, well remember this is omega A dagger A plus 1/2 acting on n. So A acting on n gives me a factor of root n minus 1. Then A dagger pulls it back up to n, but it gives me this factor. And so at the end of the day, I get an n omega plus 1/2 times n. So this is the famous formula. It's more famous if I put an h bar in, oh, excuse me, and there's an n plus 1/2, sorry, n plus 1/2 omega n, right? Yeah. So this formula is more famous if I put an h bar in front of here, but h bar is 1. So this is the famous formula for the energy levels of the harmonic oscillator. Okay? Good. Okay, so now let's come back to this idea that free fields, free scalar fields, are harmonic oscillators. All right, so let me remind you, let me write down again the formula that I had before. Sorry, let me put the time integral, 1 over v, sum over the momenta, and then we have the sum over I, going over even and odd, and then we had this 1/2 phi I dot p squared minus e sub p squared by p I squared. Okay? So this is a sum of harmonic oscillators. Okay? So each of these phi I p's is an independent harmonic oscillator. Okay? So I can, using the same construction that I just did there, each one of these is going to have its own raising and lowering operators, so there'll be some API, okay, for each one of these guys, right? And each one of these will satisfy commutation relations like this, and each one of them will have these little n's that tell us, I can take this guy, dagger to the n, acting on the ground state, and that will give me the nth excitation and so on. And so the bottom line is that if I just have a whole bunch of these oscillators, the way I have here, my states, my energy eigenstates now, are just going to be labeled by the n's of all the possible oscillators. Okay? And here really, I should find some way to say some of these are for the even guys and the odd guys, but basically for every momentum, remember for the even and the odd guys, each one of them applies to half of the p's. So I can think of there just being for every p, there's an n, which is the occupation number for that particular oscillator. Okay? And this actually looks slightly different from what we had before when we talked about Fock space. If you look back at what we did there, we were actually assuming that none of these are called occupation numbers. We always assumed that the occupation numbers were either 0 or 1. And that's actually okay because, remember, there we're dealing with momenta that are continuous. When we have continuous momenta, I think it's fair to say that we don't expect physics to care whether two momenta are exactly equal or differ in the 150th decimal place, right? And so, since the momenta were continuous, we could just pretend like any given momentum was only occupied once. Okay, so there However, if we have discrete momenta like this, we have to allow for the fact that some of the momenta can be identical, and then we actually have this occupation number representation is a little is simpler to use. And also, we didn't have these factors of root n and so on in our formulas before for Fock space, and that again was because these little n's were either 0 or 1. So that calculus, using where n's being little n's being 0 and 1, is perfectly fine for continuum calculations, but we have to be more careful here. Okay? All right. Okay, so now that we have this, we have this idea that free fields are just harmonic oscillators, we can actually finally calculate something. So let's actually calculate something interesting, all right? Yeah. So we've argued that a quantum field is an observable. That means it makes sense to measure it. So let's ask, what happens if you measure it, all right? So the state that we'll measure it in, we'll measure it in the ground state. So this may sound a little bit boring, but just wait, okay? So let's write our Hamiltonian in terms of the, for the free field, let's write our Hamiltonian in terms of these oscillator modes. And so we have 1/2, 1 over v, 1 over p, okay? And then we have the sum of I equals even in the odd modes, okay? And then we have our phi dot pi squared minus, sorry, this is the Hamiltonian, so this is the phi dot I squared plus the EP squared phi p I squared, okay? So this is a Hamiltonian, and we can see that each of these modes, pi, is a simple harmonic oscillator, okay? And the frequency of that oscillator is EP. We can see that here, right? And the, so to speak, mass of the oscillator, so this is the kinetic term written in terms of the derivatives of positions, not momenta. So the mass is actually V inverse, 1 over V, this coefficient over here, okay? And so, great, so that means that we can see that, for example, the vacuum expectation value of each one of these guys right here is 0, just like the vacuum expectation value in a simple harmonic oscillator of the position is 0, right? It's just basically because of symmetry. There's an x goes to minus x symmetry of the oscillator, and there's a phi goes to minus phi symmetry here, okay? So the field itself in the vacuum is 0. That's not so interesting. But what is interesting is to ask about the square of the field. So if we look at let's look at what we're actually interested in, which is the square of the field at the field operator, the observable, okay? And what is that, okay? Well, in the simple harmonic oscillator, this is going to be a sum of terms that involve the square of x. And in the harmonic oscillator, the square of x is given by 1 over 2m omega, okay? In a harmonic oscillator of mass m and frequency omega, we could derive this pretty easily, but let's not stop to do that, okay? And so this translates into a result for the product, okay, of an arbitrary pi q j, okay? If we take an arbitrary product of these oscillators right here, first of all, it's only non-zero if p is equal to q, right? And if I is equal to j. Simply because if that's not the case, then this is just the product of two completely independent oscillators, and those vanish just because it's the product of things like this, right? Now, if it's not 0, it's this thing right here, which is a 2 over EP, and then there's a volume on top, right? Using this dictionary here that we have between the harmonic oscillator and these oscillators right here, okay? Okay, so now using this result here, we can go ahead and plug in, excuse me again, we can plug into the field, okay? And the field, phi of x t, given by an expression like this, 1 over v, there's a sum over p, there are my, there's my cosine terms, p dot x, phi p even, plus my sine terms, p dot x, phi p odd, okay? And these are functions of just t, right? Okay, so this is writing my field as a sort of Fourier transform of these various oscillators, right? And now what I want to do is look at the vacuum expectation value of the square of x, right? And so I'm going to get a 1 over v squared. I'm going to get two of these sums right here, but this delta function collapses them down to 1, okay? And so I'll just have a sum over one of the p's. Then I'll have the product of the cosine, so cosine squared p dot x, okay? Then I'll have the product of two fields like this, which is this factor of v over 2ep, okay? So I have a factor like that for the even guys, and I have a factor like that for the odd guys, p dot x, v over 2ep, okay? Right? Now this obviously simplifies. One of the volume factors cancels. The cosine squared plus sine squared is 1. They both multiply the same thing. And I get a vastly simpler expression, which is just 1 over v, sum over p, just 2 ep. Okay, that's it. Okay, and if to interpret this, let's go ahead and take the infinite volume limit. This is d cubed p, 2 pi cubed, 2 ep. Okay? And this integral is very easy to do. It's infinite. Why is it infinite? It's infinite because I have basically 3 powers of p upstairs, and this is linear in p. So it actually this integrand diverges, it diverges quadratically with large p. So the problem comes at large p, and it just diverges. Okay? So the answer is that the fluctuations in this field seem to be infinite. And this arises because there are fields to arbitrarily large, there are modes with arbitrarily large momenta, and that in turn comes from the fact that we had locality, that we had a mode at every single position. So the locality, which was something which was really, we argued, was very fundamental to having Lorentz invariance, has led us to infinities. Okay? And this is a problem that we won't fully be able to grapple with in this quarter. In fact, we'll mainly ignore it in this quarter, except for the rest of this lecture. So I'm going to do a few more calculations, and I'm going to try to at least convince you that these infinities are real. As we understand them, as the way we understand these things is that these are telling you what they seem to be telling you, namely that you calculate these quantities, they are extremely sensitive to the structure of the theory at very, very short distances, right? However, we may not know exactly what this is, so perhaps these extrapolations that we made are not correct. And so we have ways of dealing with that, but not today, not now, certainly, okay? So for now, let's try to get a little more intuition about this by computing something that is finite, okay? So this thing was infinite, but we can compute a smeared field. So we can define a smeared field. We'll call it phi sub r. So r is actually stands for some region, some spatial region, right? So we can imagine in space there's some region r, okay? And the way we define this is a function only of t, is we integrate over this spatial region phi of x and t, and then we just divide by the volume of this region. So v of r is the spatial volume of this region. So in other words, we're averaging the field over a finite size region. So if the idea is that if there's an infinity due to this locality, by smearing the field here like this, we should get a finite quantity, okay? And so now what we can calculate is we can calculate the square of this smeared field, right? Okay? And what is that? Well, we have to do this average twice, so we're going to have a 1 over VR squared. We're going to have a d cubed x over r, d cubed y over r. We're going to integrate over this region twice. And for each of these regions right here, we will have, we're going to compute something like this. Okay? And so what we see is that in order to compute this quantity, we have to know the 2-point function, the expectation value of the product of fields at space-like separated points x and y, right? Because we're calculating all of this at the same time. Okay? And so let's calculate this quantity right here. This is phi of xt, phi of yt. What is that? This quantity here? Well, we're going to get 2 of these volume integrals, right? We're going to get a sum over p and q. But again, remember that this is going to be, we're going to get, here I've erased the rest of this up here, but we know from the 2-point function we're only going to get a non-zero thing if the p's are the same and the even in the odd terms, right? So we're going to get something like cosine p dot x, cosine p dot y, okay, because these x's and y's are certainly different. And then we're going to get our factor of v over 2 ep, and then we're going to get the same thing with sines, sine p dot x, sine p dot y, and again with the 2 v over 2e of p, okay, like this, okay? And once again, that simplifies, so now let me erase this, okay, and continue up here. What is this going to be here? Well, I'm still going to have my 1 over, well, so there's this v again that cancels one of these v's down here, so I'll end up with just a 1 over v, and I have this p, and these two things here combine to give me a cosine p dot x minus y, okay? That's this cosine, cosine, sine, sine business. And then I have 2et, okay? And this has a nice continuum limit. If I take L goes large, this becomes cosine p dot x minus y 2e of p, okay? Now, actually, this you can actually show that this does converge at large p. Basically, this oscillates faster and faster, and it causes this thing to actually converge. Okay. Now, we could actually go ahead and finish computing this, but I just want to make some rough estimates. Remember, my region R. Well, let me also call the characteristic spatial size of it R. So now I'm just going to do order of magnitude estimates. I'm going to assume that R is much smaller than M inverse. Okay, so R is actually smaller than the Compton wavelength of this particle of mass M. And that actually means that I might as well, in computing this, I might as well take M goes to 0, because the idea is that the wavelengths of the p's that will be important will be such that E of p can just be approximated by just p, just the magnitude of the vector. Okay, and so then if I do that, then what I see, because there's essentially there's no scale other than if I look at this 2-point function, which I've been evaluating, this thing up here. Since there's no other scale, this thing has to be proportional to x minus y, 1 over x minus y squared. So I just got this from dimensional analysis. So you can see here, this has units of mass cubed. This has units of this is 1 over mass, so this has units of mass squared. And since it only depends on this difference, x minus y, it has to be proportional to this. Okay? And then, if I plug that back into my expectation value of the squared field like this, okay, then I'm going to get 1 over r squared. Okay, the exact prefactor will depend on the exact shape and so on, but it'll be of order 1 over r squared. Okay, and this is again just by dimensional analysis. You can see here, backing this thing out, you can see, oh yeah, well, this is equivalent to saying that the fields have units of 1 over length or mass, and so this averaged field has the same units, and so by dimensional analysis it has to be this. And notice indeed that this does go to infinity as r goes to 0. So if I measure the fluctuations of the field averaged over shorter and shorter distances, it will get larger and larger without bound, and it'll eventually blow up. Okay? So at the end of the day, this is all really just dimensional analysis, right? And that means that I can actually immediately see what the result is for any dimension. Okay, so having seen that it's just dimensional analysis, let's go back all the way to the action. Okay, so what does the action look like? In d dimensions, let's look in d, capital D, space-time dimensions. Then what this looks like is 1/2 d mu phi, right? And then I have, well, other terms. But if I look at this and realize that the action has to be dimensionless, okay, and that actually comes from the canonical normalization of the fields. If you work that out in any dimension, the action is dimensionless in our units, where everything is mass. And that tells you that the dimension of this thing is d minus 2 over 2. So here when I write the dimension equal a number, this is the power of mass that is the dimension of that object. Okay? And from this you immediately see that, okay, if I want to calculate phi squared of r, here I'm just calling the average like this, that this is just going to look like 1 over r to the d minus 2. Okay? So if I go to lower dimensions, okay, then this divergence as r goes to 0 is actually less rapid. Okay? And so one case that is of some interest here is actually the case d equals 2, which is 1 plus 1 space-time dimensions. And in d equals 2, this power vanishes, but really this is a log, because it's a log, this is a log divergence. And so what I get in 2 dimensions is that this thing looks like 1 over log r. Okay? So this diverges slowly as r goes to 0, but the flip side of that is that for large r, it actually dies off slowly. So fluctuations in 2 dimensions averaged over large spatial regions only die off like a logarithm. So these fluctuations are very important. Okay? And actually, if you follow this through, one of the implications of this is that these fluctuations are large enough that they actually prevent the formation of long-range order, or in particle physics language, spontaneous symmetry breaking. So this is the Coleman-Merman-Wagner theorem. It's a theorem that holds, there's a version of it that holds in quantum field theory, and a version of it that holds in statistical mechanics. And these two things are connected to each other by analytic continuations, one of the things I mentioned in the introductory lecture. Okay, so anyway, this just tells you that very simple dimensional analysis can actually tell you something very, very basic about the field as an observable. Okay? All right, good. Okay, one last topic for this lecture, the vacuum energy. All right, so let's look at the expectation value of the Hamiltonian in the ground state. Okay, well, this is very easy because for every momentum, p, we have an oscillator with, and its frequency is e sub p, so we just have to add up 1/2 e sub p for all of the p's. Okay. Now, remember, there's this little subtlety that there are even oscillators and odd oscillators, but for each one you only sum over half of the p's, so this is actually correct. The factor is right. Okay? Now, notice that there's no 1 over v here, so the continuum limit looks a little funny, But then if you think about it for a second, you realize, no, that's right, because what I expect to be the correct quantity to think about in the infinite volume limit is the vacuum energy density, all right? Because every point in space is like every other point in space, so there should be a uniform energy per unit volume. And so that would be the expectation value of the Hamiltonian divided by the volume, and that's just the volume times this, 1/2 e sub p. And this is a quantity which does have a good limit as L goes to 0, or the volume goes to 0. It's d cubed p 2 pi cubed. There's a 1/2, which I'll pull out, and then there's a p squared plus m squared. Okay? So I should have said this before. This is the sum of the 0-point energies, the famous 1/2 h bar omega, for each of the harmonic oscillators. Okay? And so here it gives you this energy per unit volume. Okay? And once again, this is an easy integral to do, just like the last one. The answer is it's infinity. It's UV divergent. Okay? So now, this time let's go a little bit further in actually evaluating this. Okay? So what do I mean by evaluating it when it's infinite? Well, the basic idea is that we say, you know what, I'm not sure I believe this theory is valid for arbitrarily large momentum p. Okay? Because I haven't tested it there. So let me just cut off this integral, okay, take this integral and cut it off, okay, for p, so by integrating only over p, 3 vectors p whose magnitude is less than some lambda. And I'll choose this lambda, this is some mass scale, and I'll choose it to be much larger than anything that I've ever measured. Okay? And then when you do that, so if you just, this is an artificial mutilation. Let's be clear about what this is. It's just, you're just mutilating the theory, but the only justification is you're mutilating it at short distances, so maybe that's okay. Okay? And what happens if you do that? What do you get? Okay? Well, you get that the vacuum energy, now you can do this integral, and I won't do it in front of you, but I'll tell you what the answer is. You get something, you basically get what you would expect from dimensional analysis. This thing depends on m and lambda. Those are the only 2 dimensional full quantities on which it depends. It has units, if you look at this thing, this has units of mass to the 4th, so it'll be some function like this. And now I'm expanding it for lambda much bigger than m. Since I'm looking at, I want lambda to be bigger than every physical scale, it must be bigger than m. So for the leading term is lambda to the 4th. What else would it be? And then there's a lambda squared m squared piece, and then there's an m to the 4th piece with a prefactor, I think it's, minus a half, okay, log 2 lambda over m. See, so I'm expanding in large lambda, and then the terms that I've left out are of order m to the 6th over lambda squared. So the terms that I've left out, instead of being big as lambda goes to infinity, they're actually small. Okay? Okay, so what does a calculation like this mean? Well, okay, so what we believe is that, you know, this cutoff here is certainly nonsense, but something should come in and make this theory finite, perhaps some new kinds of physics or something. And we actually have models like that, okay, so it's far down the road from where we are now. But some sort of physics has to cut this off, and it has to be associated with some scale. And if we evaluate this thing in that fundamental theory, this integrand will be as it is here for p much less than lambda, and then for p above this scale lambda, it'll be something different. And so the answer has to look something like this. In particular, it has to have this huge lambda piece here. It has to have this huge m-dependent piece. It has to have some form like this. That's what we believe. Okay? All right. Now you might say, okay, but who cares? Because you can't observe the energy of the vacuum. The vacuum is the lowest energy state. Okay? So if I say that the lowest energy state has some huge vacuum energy that has no observable consequences, all I can measure is the differences of energies. Okay? And that sounds like a reasonable argument, but it's actually not correct. Okay? And one reason is that some of these divergent pieces, these terms that diverge when lambda goes to infinity, depend on m, mass, okay? And for example, in the standard model of particle physics, the mass of all the elementary particles is actually proportional to a field, the Higgs field. And if you trace all of that through, it turns out that this m-dependent contribution to the vacuum energy actually corresponds to a field-dependent contribution to the energy of the system. And that's something you certainly can measure, because if you change the field, you change m, and then you're changing the vacuum energy by this divergent amount. In fact, precisely this kind of a contribution right here, where this m comes from a Higgs, is exactly one of the manifestations of this problem that I alluded to in the beginning, in the first lecture, which is that the Higgs in the standard model gets these huge contributions to its mass from the fluctuations of other fields. And this is exactly a manifestation of that, where if this mass, this particle that we're computing here gets its mass from the Higgs, this term translates into a contribution to the Higgs potential, which is huge, okay? So it can be observed. And there's another context in which this can be observed, and that is if I turn on gravity. If I turn on gravity, it is no longer true that only differences of energies are observable, because a constant term in the action still depends on the metric, and it is, in fact, exactly the so-called cosmological constant term. And so even this huge term, this quartically divergent term, contributes directly to the expansion of the universe. And I talked a little bit about this problem here for the Higgs and said that, well, we have a couple of solutions, but we're worried if any of them is right. For the cosmological constant problem, we have no solution. It seems to be a really deep problem, and as best we can determine, it may really be a kind of cosmic coincidence. Okay, so that's it for now.